Welcome to the 953rd monthly meeting of the Amateur Telescope Makers of Boston. This is my last meeting as president of the club. Our guest speaker tonight is Phil Levine. He's going to talk about Sir Fred Hoyle and give you some perspectives on his work. Glenn Chappell is not here tonight, so I am going to give the observer's report. This is the cartoon he sent me in honor of our speaker tonight. Phil Levine is going to talk about Fred Hoyle, who was almost a lone proponent of the steady state theory of cosmic evolution. So Glenn said, "Oh, I've got lots of great cartoons on that." So there they are, chuckle, chuckle, ha ha. Here's his quote. I had nothing to do with this, but the fate of human civilization will depend on whether the rockets of the future carry the astronomer's telescope or a hydrogen bomb. Sir Bernard Lowell, I don't know when that quote was made, but sure, of course. You know, the nice thing about the hydrogen bomb part is makes me think of hydrogen fusion inside the sun. And as you'll hear later on, Fred Hoyle was one of the physicists who actually worked out the mechanisms for nucleosynthesis in stars, which is one of my favorite things to talk about. So more about that later. Now let's see. So here's my annual report for the observing committee. Of course, you know, everything had to comply with everything we went through with COVID. So Glenn Chappell and Rich Nugent continue to present the monthly observers report at our meetings. And Rich Nugent continued to email his 19+ objects to observe and predictions for Jupiter's great red spot transit times and shadow transit times for Jupiter's 4 large satellites to the membership. I plan to continue to do that for the long haul. As mandates and restrictions evolved, observing sessions were held at the clubhouse. However, no specific member events were held. And if you read my president's message in the newsletter, one of the things I talk about is having more members events at the Westford site. So go read about that, and you'll hear more about that from me as we go forward. Of course, we had a total lunar eclipse on May 15th and 16th, and we got some nice images from some of our members. I'm not going to ask people to chime in. They're beautiful. Thank you, Sal and Mark and Bert and Joseph, for these fine images of the eclipse. The one of Sal here makes me remember that, oh yeah, I stood in the rainy cloudiness for about an hour and a half waiting for a break in the overcast. And I actually got to see about 30 minutes of the last 30 minutes of totality. So I felt pretty happy that I duked it out and waited for the clouds to subside a bit. And then of course it was swallowed right back up again. But it was a beautiful eclipse. It was relatively dark. And I hope everybody got a chance to go out and observe it. Bruce Berger was in Oregon, and this is a great shot he sent, the moon peeking through some lone breaks in the overcast. And Doug Paul sent us this image here, which really shows nicely that this is really what it looked like by the time I caught up with it, with the limb here being a sort of creamy white as it approached the edge of the umbra, and the nice dark umbra here with the nice orange colors. So thank you everyone for submitting images of the eclipse. The next one is in November, a pre-sunrise eclipse. The moon will set here in New England during totality. So that might make some interesting photo opportunities for folks. So stay tuned for more information about that. November 7th, and I think it's either the 7th or the 8th. Here are the observing highlights for the next month. There's not much going on, but on Thursday, June 16th, Mercury reaches greatest elongation west, 23 degrees west of the sun. That means it's in the morning sky. And so with the parade of planets going on, Mercury joins in the parade for a brief period of time mid-month. On the 18th, the moon is 6 degrees south of Saturn at dawn. On the 21st, we have the summer solstice at 5:14 in the morning, and the moon is 5 degrees south of Jupiter that morning. Look again, southeast just before dawn. Looking ahead, at mid-month in June, Jupiter is sporting a 40 arcsecond diameter disk. Opposition is on September 26th, and right about then, I'll start sending out all my predictions for Jupiter. Saturn transits at about 5 in the morning, Eastern Daylight Time. The rings are inclined 12.4 degrees. Opposition is on the 14th. Mars is a teeny tiny 7 arcseconds, but opposition is coming up in December, early December, when the disk of Mars will be a little over 17 arc seconds. That's a pretty favorable opposition. It'll be pretty high in the sky as well. Venus is at superior conjunction the sun, October 23rd. Let's see, what else do we have here? Oh, Glenn would be smiling right now. He will be when he sees this presentation, because he loves this star SS Cygni. It's been one of the most closely followed variable stars in the history of variable star observing. It's a cataclysmic variable where a white dwarf is pulling in matter from a red giant star. The surfaces are thought to be only about 100,000 miles apart. And as material piles into the accretion disk of the white dwarf, you see the changes in brightness. And they're running right now about once every month. And so looking ahead, the weekend of June 25th would be the next time to look for it. Here's Cygnus the Swan here. This is rising in the east about mid-evening. Rho Cygni is there, and SS Cygni is right here. I start by finding Rho Cygni, and then I hop over to 75 Cygni, which is only a full moon's diameter away from this triangle of stars right here. And SS Cygni lies right there. Glenn likes to observe that star with a telescope, unable to see 12th magnitude stars. So he'll look at this triangle and wait for SS Cygni to break the barrier of his telescope. And then he knows it's an outburst. So I encourage you to do the same thing. Go find that star. Once you know where to look, you can get your telescope on there easily, and you can monitor it every clear night, and you can see it go through an outburst. They're kind of fun to watch. Glenn will be very happy to hear we talked about that. The observer's challenge for June is NGC 5474, which is a faint galaxy in Ursa Major, very close to M101 right here. This is Alcor and Mizar, 81, 83, 84 to 86 Ursa Majoris, leads you to the vicinity of M101, and this galaxy is to the southwest. So in this sketch, I tried to get Glenn, I tried to contact him. I don't know who made this sketch, but there's M101, and there's the galaxy we're talking about. It's faint. It is a challenge, but I encourage you to go out and look for it. Some of the members have sent some interesting pictures. Doug Paul sent us this image of the galaxy. Very nice. Mario Mata with his 32-inch. I think that was a 32-inch scope. Excellent. Here's M101 here in Dave Russ' image. There's the galaxy, the challenge of the month right there. So you can see how close it is to M101, which in itself is a very difficult object, in my humble opinion. And the last picture is by Chris Elledge, taken with the Middleman Observatory up at the clubhouse. And Glenn offered this sketch right here, and I think he put it in because he wanted to point something out. I know they may be hard to see, but there's a little triangle of stars right here. These two stars in his sketch are 12th magnitude stars, as is this star right here. Now look what the Middleman telescope can do. Here are those 12th magnitude stars. There's the pair of them, and there's this little guy here. And look at how deep the Middleman image actually goes. Chris, do you recall how long of an image that is?
Well, it's 2 hours of luminance integration.
Okay.
But each exposure, I think, is only 2 minutes.
Okay. Well done. There's even a little galaxy right here. It's very hard to see, but that's somewhere in that little knot of light right there is another galaxy. That's pretty cool. Thank you for submitting that, everyone. Those pictures, everyone. And there's Glenn's sketch again. That was with a 10-inch telescope. And finally, to offset the difficulty of NGC 5474, the July object is the Turtle Nebula, NGC 6210 in Hercules. I don't know who submitted that picture on the right, but here's the keystone of Hercules. And so beta is down here, and the object is right here. It's bright enough so that with a 50mm finder, you should be able to see that in the finder scope. And it's got a very pretty bluish green color. So I encourage you to go look at that. If sometimes we write off the NGC objects because we think, well, they're NGC objects, they must be faint. That's a pretty bright one right there. So I encourage you to go out and take a look at that. All right, tonight's speaker is Phil Levine. We'll speak on Sir Fred Hoyle to give us some perspectives. Phil earned a BS in history from Northeastern University and a certificate of electronics technology from the Lowell Institute School, which is a branch of MIT. Now retired, he worked some 43 years at Peter Bent Brigham and Women's Hospitals in various capacities, but most notably as a cardiac cath lab technician. Phil also spent many years as a technician in the hospital's Clinical Engineering Department. He is also a certified biomedical engineering technician emeritus, and Phil has done work with the CFA's glass photographic plate digital conversion project and has served as the ATMoB Secretary from 2015 to 2018. So a little different this time. I'm going to try and run Phil's presentation from here. And we are going to cross our fingers that this is going to work. So I am going to stop sharing. Then I'm going to start sharing again because I want to get to this screen. I want to share sound. We're going to flip back and forth between this screen and the next. So slideshow. And we already went through some slides, didn't we, Phil? There you go.
Okay. Am I audio?
I can hear you just fine.
Well, that's good. Okay. Well, here we go. We are keeping our fingers crossed. So when I started putting together this presentation, I thought it was going to be relatively easy. But as I read more source material, books, published papers by Hoyle, became clear the presentation needed to include other astronomers, cosmologists, and some current research data. Some of Hoyle's ideas remain quite controversial. So thanks for your intro, Rich, and thanks for all you have done as club president. Appreciate it very much.
Well, thank you.
So next slide, please. I'm not going to go through all the bullet points. These are the career highlights of Fred Hoyle. I will point out at the bottom where it's annotated in red, Nobel Prize ? He did not receive a Nobel Prize, and I will be going into a little detail on this later on in the presentation. The next slide, please. So just a little bit of background on the education of Fred Hoyle. He was a product of the English school system. His family was what we might consider middle class. Early in his education, Hoyle showed an independent, almost rebellious spirit. He played hooky after a disagreement with his teacher. And instead of going to school, he visited the Canal Engineering Works near his home in Gilstead, West Yorkshire. An influential teacher saw promise in Hoyle and helped him to apply for a scholarship to a better school system. And I'm going to insert something here. When he was attending at the college level, he was not the greatest in mathematics. And he really applied himself. And at the end of his college education, he was near the top of his form in math, but he attended Emmanuel College, St. John's College in Cambridge. Influential educators, Maurice Price, Paul Dirac, Arthur Eddington, James Jeans, Ralph Fowler, visiting professors, Werner Heisenberg, Niels Bohr, Wolfgang Pauli. So he received an education at a very influential period in cosmology, astronomy, and during the dawning of quantum mechanics. Next slide, please. After he graduated, Hoyle made a significant contribution in World War II, which I feel perhaps was one of the considerations which led to him being knighted later in his career. So there was an issue during World War II with the accuracy of British radar, and Hoyle helped problem solve that. The British used 7-meter wavelength Type 79 radar, which worked well for range, but was not always accurate for detecting altitude. So what Hoyle did was he formulated 10 experimental performance test graph curves, and then incoming British test aircraft that were flown at a known altitude were then utilized. And Hoyle chose the graph curve which best fit the aircraft range. And that graph was instrumental, crucial in the British naval battle victory against an Italian fleet at Cape Natapin. Next slide, please. Early cosmology contributions in the late 1940s with Tommy Gold and Herman Bondi. Tommy Gold and Herman Bondi were two colleagues that did radar research along with Hoyle during World War II. And the story goes that the three of them got together at one of their flats to discuss astronomy. They had some liquid libation. I don't know exactly what they were drinking, but they came up with the first revision of the steady state theory. The steady state theory held the universe is eternal and matter concentration could be perceived as being uniform throughout, having no origin in time. An essential concept, the universe is expanding due to the continuous creation of matter. And this was very controversial, that how can matter be created? It seemed at variance with the standard thought on physics. The steady state theory was widely criticized by the astronomy community at the time. The evidence of cosmological redshift did not seem to validate the steady state theory. As most of us know, Fred Hoyle coined the term Big Bang, but he meant it as a disparaging remark because he felt the theory was wrong. Next slide, please. These are the three, Hoyle, Tom Gold, Herman Bondi. Thomas Gold later became a professor of astronomy at Harvard and then at Cornell. Herman Bondi was an influential administrator at various astronomy sites throughout Europe. Next slide, please. Now, a cartoon, and Hoyle is speaking to a microphone with the BBC abbreviation. Hoyle did a lot of talks on the BBC popularizing astronomy to the general public. And as is mentioned in this cartoon, he felt it was ridiculous that the Big Bang was everything that could explain how the universe came to be. Next slide, please. The Big Bang timeline. I think it's important just to outline the Big Bang. We're probably familiar with most of it, but I'm going to run through this briefly. Alexander Friedmann, 1922, published solutions to Einstein's equations of general relativity. George Lemaitre also published solutions to Einstein's equations of general relativity in 1927, 1931. Lemaitre proposed the origin of the expanding universe resulted from a primeval atom, which was extremely dense, exploded, and expelled hot particles of matter, expanding out from this point of singularity. Edwin Hubble's landmark calculation determining the distance to the Andromeda Nebula in 1925, determination most galaxies are receding, indicating expansion in intergalactic space. George Gamow, in 1946, made a prediction of a primordial radiation relic. 1965, Penzias and Wilson detected the cosmic microwave background radiation. 1965, Robert Dicke stated the cosmic microwave background is a remnant of the primordial fireball. Later, and actually Stephen Hawkins, 1966, his thesis on black holes, and Roger Penrose, gravitational singularity, made contributions. Verification of the cosmic microwave background radiation by COBE, and I'm going to minimize Rich, the M.I.T and the Planck probes. Next slide, please. This is a well-known graphic, courtesy of NASA, which shows the timeline explanation given by the Big Bang. singularity, development of galaxies, planets, Big Bang expansion. Next slide, please. So here is yet another alternate theory of how our universe began. And it's poking fun at the Large Hadron Particle Collider. And I remember back before the Large Hadron Particle Collider came online, there was concern that what might happen if we smash these particles together? Might this create a black hole and a major catastrophe? And I guess we're still here, so we kind of have put that one behind us. Next slide, please. Cosmological thoughts. Next slide, please. So I'm not going to read these bullet points other than show the dates involved, starting in 1946, the 40s, 50s, 60s. I believe in the 70s, Fred Hoyle was an active administrator and was rather busy. The 80s and the 90s. I'm going to be going into some detail on some of his papers and presentations later in the presentation. Next slide, please. An early paper in 1946, The Synthesis of the Elements from Hydrogen, which was submitted to the Royal Astronomical Society. In this early paper by Hoyle, he outlined a process of nucleosynthesis, which can lead to the production of many of the elements past atomic weight 40 in the periodic table. So there had been others that had theorized on the process of nucleosynthesis, but it wasn't really, it could not be confirmed to the extent that later work, especially by Hoyle, was able to show via various calculations, spectroscopy, and later with the collaboration of a couple of his colleagues. So next slide, please. A new model for the expanding universe in 1948. The summary he gives here: by introducing continuous creation of matter into the field equations of general relativity, a stationary universe showing expansion properties is obtained without recourse to a cosmological constant. So I'm going to read the beginning of the paper because I think it's very insightful. Creation of matter was mentioned about 20 years ago, which would have put it about 1928, by Sir James Jeans, who remarked, the type of conjecture which presents itself somewhat insistently is that the center of the nebula, galaxies, are of the nature of singular points at which matter is poured into our universe from some other and entirely extraneous spatial dimension, so that to a denizen of our universe, they appear as points at which matter is being continually created. So I think this is a pretty remarkable speculation by Sir James Jeans in 1928. There certainly was not the technology at the time, certainly not the optical telescopes. There were certainly no orbiting probes or satellite telescopes to provide any data. Yet here is he's making this really remarkable conjecture. Next slide, please. In 1953, Hoyle made a theoretical prediction stating carbon-12 must have an energy state of 7.65 mega electron volts in the nucleus as a result of 3 helium-4 nuclei, beryllium, and a triple alpha process. This was confirmed via experiment a few years later by Willie Fowler at Caltech. So I'm going to mention here, Willie Fowler, at first, when Hoyle made this request to him, absolutely refused. He thought it was a ridiculous speculation that an astronomer could tell a nuclear physicists to look for this energy level of carbon-12. And Hoyle was a rather stubborn fellow, and he persisted, and Willie Fowler agreed, and he did find it at Caltech. The next slide outlines how Hoyle was able to make this prediction. This is a still from a video that I hope we will be able to show tonight.
Ready to give it a try?
Well, before we try it, what I was going to mention is I always had a bit of difficulty grasping the full extent of the significance of subatomic particles to astronomy. And this video really explains at one particular point how important this is to astronomy. So let's give it a go.
All right, cross your fingers. Let's see if this works.
It's the basis of all known life, and
Can
it's
you hear
the
that?
universe's fourth most abundant
Okay.
element. However, it can only be made because the behavior of matter seems to be rather finely tuned to permit its existence. Make of that what you will, plenty of people have. In the early part of the 1900s, people thought stars shone by shrinking and converting gravitational potential energy to heat. In fact, this is the way they heat up in the first place, but it's not the main source of their energy. In 1920, Arthur Eddington likened the contraction theory to an unburied corpse. He noted that the sun, by fusing hydrogen to helium, would convert mass to energy. It would therefore have sufficient fuel to shine for billions of years. In 1939, Hans Bethe filled in the details of the proton-proton chain reaction, explaining how the sun gets energy by fusing hydrogen into helium. He also unveiled the CNO cycle, which explained how massive stars convert hydrogen to helium. Although Bethe's CNO cycle relied on the existence of carbon, he had a problem. He couldn't find any reasonable way that elements heavier than helium could be made. Bethe investigated the possibility of making carbon by bringing together 3 helium nuclei, alpha particles. He found that the process would need temperatures of more than 1 billion Kelvin. This is pretty high. Our sun's core is about 16 million Kelvin. He assumed the coming together of 3 alpha particles was a non-resonance process. What do we mean by a resonance or non-resonance process? These concepts are crucial to carbon's existence. Think about the traditional Bohr model of a hydrogen atom with an electron behaving like a little planet orbiting a nucleus. The available orbits represent the energies an electron is allowed by the rules of quantum mechanics. We can draw these energy levels like this. In this hydrogen atom, the electron is in its lowest possible orbit, the lowest energy state, the ground state. If the electron picks up the right amount of energy from somewhere, it can move to a higher orbit, one of the possible excited states. In this story, we're not dealing with electrons, we're dealing with nuclei and their energy levels. Just like electrons, nuclei are governed by the laws of quantum mechanics and have permitted energy levels. These are shown here for carbon-12. Nuclei have ground states and excited states. The energies involved are much higher than electron energies because nuclear masses are so much greater. We're dealing with a scale of millions of electron volts. These are nuclear mass energies. They are fixed and independent of the speed of a nucleus. They don't vary with temperature. The kinetic energy varies with temperature and isn't included in these numbers. Now, back to our tale of how to fuse lighter nuclei to make carbon-12. Nuclei are all positively charged and repel one another electrostatically. For nuclear fusion to happen, we need to overcome the Coulomb barrier erected by this mutual repulsion. The trouble early researchers had was that even in the sun's core, the temperature wasn't high enough to give nuclei enough kinetic energy to overcome electric repulsion and fuse. George Gamow showed the way in 1928, explaining alpha particle decay with nuclear quantum tunneling. The following year, Robert Atkinson and Fritz Houtermans showed that quantum tunneling allowed nuclear fusion to happen. Quantum mechanics treats atomic scale particles as probabilistic smudges. These can occupy space that they couldn't if they were sharply defined classical particles. Nuclear fusion happens because nuclei tunnel close enough together to merge. quantum tunneling is optimal when products and reactants have similar energy levels. In other words, when they're in resonance. The reaction's probability increases greatly when there's resonance. The energy level of the products needs to be a little higher than of the reactants because the kinetic energy needs to go somewhere. Now, back to Hans Bethe's problem. The universe shouldn't have much carbon because its non-resonance formation from 3 alpha particles needs a temperature of 1 billion Kelvin. Ed Salpeter thought about changing the picture. Rather than 3 alpha particles colliding, he pictured 2 colliding to make beryllium-8. Beryllium-8 then collides with a further helium nucleus to make carbon. In 1952, he observed that the mass energy level of ground state beryllium-8 was only slightly higher than the energy of a pair of alpha particles. He reasoned that this would lead to an important resonance. Beryllium-8 is highly unstable and it decays back to 2 alpha particles with a half-life of about 10 to the negative 16 seconds. The resonance is enough to make an equilibrium concentration of beryllium-8. Salpeter argued that this permanent presence of beryllium-8 nuclei allowed them to fuse with further alpha particles to make carbon. In 1939, Bethe had reasoned that carbon production needed a temperature of 1 billion Kelvin. Salpeter's work reduced the temperature needed for carbon by a factor of 5 to 200 million Kelvin, a temperature achievable in the contracting core of a red giant. In the early 1950s, Fred Hoyle probably knew more than anybody in the world about element formation in stars. He liked Salpeter's idea that triple alpha production of carbon could be helped by an alpha particle beryllium-8 resonance. He didn't like the idea of 200 million Kelvin. Carbon had to be made in greater quantities than Salpeter's work allowed, and at about 100 million Kelvin. Hoyle compared the mass energy levels of a beryllium plus a helium nucleus and a carbon-12 nucleus. He calculated that if carbon had an available energy level at about 7.7 million electron volts above its ground state, then there would be a resonance with beryllium and helium. Carbon production would get a huge boost. The boost was necessary because without it there would be no carbon to make physicists to study the problem. Early in 1953, Hoyle asked Willie Fowler and his team of nuclear physicists at Caltech to look for it. This might have appeared crazy, an astronomer telling nuclear physicists that they'd missed one of carbon's energy levels. Nevertheless, Fowler's team looked for the energy level and found it. It's this energy level that allows carbon to exist, and you and me with it. The Hoyle excited state of carbon is more like a loose bunch of 3 alpha particles than a fully merged ground state carbon nucleus. The great majority of excited Hoyle state carbons fall apart again into beryllium and helium. About 1 in 2,400 Hoyle state carbons fully merge into carbon-12, emitting huge amounts of energy. Even today, the behaviour of the Hoyle state continues to intrigue researchers. Hoyle made another prediction. If an alpha particle adds to carbon, you get oxygen. If this fusion reaction was resonant, nearly all the carbon ever made would have ended up as oxygen. Hoyle said therefore that oxygen has no energy levels available for a resonance with carbon and helium. He's been proven correct in this too. Some scientists, including Hoyle, later argued that the triple alpha process has a deeper interpretation. The universe looks to be improbably fine-tuned. The narrow resonance bands without which there would be no beryllium-8 and carbon were evidence of this. They are so delicately arranged that there's little room for variation. Do the delicate patterns imply that the universe had an architect? I'll leave that question to you.
Thanks, Rich.
All right, let's see if we can get back where we want to be.
You'd think it was easy to make carbon. It's the basis of all.
While Rich is getting back into the slide, oh, there we go. Wow.
Look at that. It actually works, Bill.
Hey, I think there's something remarkable in the video. It shows that there was early research by Hans Bethe and later Edwin Salpeter, and the calculation of the energy level, it wasn't correct. Initially, it was 1 billion Kelvin. Salpeter refined it down to a lower temperature. Hoyle nailed it. And this is something, I guess, that often happens in research. People build upon other people's work, they refine it, and it all works out in the end. So here we have a landmark paper, 1957. This is a famous paper that Hoyle, who was largely considered to be the main contributor in this paper. The Synthesis of Elements in Stars, 1957. He did this in collaboration with Geoffrey Burbidge, Margaret Burbidge, and Willie Fowler, his buddy at Caltech, who helped him with the carbon-12. So the 1957 B squared FH paper, as it's widely known, described the stellar nucleosynthesis process by which elements from helium to uranium are formed within stars. So stellar nucleosynthesis was speculated upon by previous astronomers, but in this paper, it really spells out via calculations. You've got Willie Fowler, who is a nuclear physicist, Geoffrey and Margaret Burbidge, who contributed spectroscopy, verification of Hoyle's ideas, and they all collaborated on this. So the B squared FH paper served to incorporate and update previous incomplete theories of nucleosynthesis in stars. Previous stellar nucleosynthesis paper presented limited explanations. So Willie Fowler was actually awarded a Nobel Prize for this. And I'm going to get into some detail. It may be in the next slide. Thank you, Rich.
I want that now. There you go.
So here's Fred Hoyle in front of the periodic table of the elements. And I just have to say, thank you, Fred. So we'll go to the next slide. So Willie Fowler wrote a letter to Fred Hoyle after he was awarded the Nobel Prize. And he expresses initial elation at receiving the Nobel Prize and then regret that Hoyle at least did not share in the Nobel Prize. But Willie Fowler felt obligated to accept the prize because of the work done at Caltech in the Kellogg Radiation Laboratory. He did not want to let his colleagues down. So next slide, please. So I'm going to get into a little bit more of the background about perhaps why Fred Hoyle did not receive the Nobel Prize. Because Hoyle actually criticized, there was awarded to Martin Ryle and Anthony Hewish. They were awarded a Nobel Prize in 1974, which their work largely dealt with quasi-stellar objects. And as the story goes, Jocelyn Bell did her thesis, and she is attributed with discovering quasi-stellar objects. This was part of her thesis. A description of the discovery of pulsed radio sources is given. So Hoyle actually vocally criticized Martin Ryle and actually sort of accused him of plagiarizing Jocelyn Bell's work, which led to a lawsuit against Hoyle by Ryle and a subsequent public apology by Hoyle to Ryle. But in criticizing the Nobel Prize Committee, I guess you don't do that. And they probably held somewhat of a grudge against Hoyle, and that may have been one of the reasons why he did not share in the Nobel Prize for the B squared FH paper. Next slide, please. So the steady state theory kind of evolved over time. As data came out that kind of shot down the steady state theory, a quasi-steady state cosmology theory developed. And this seems to be a continuously updated theory. So expansion of the universe, according to Hoyle, is caused by a negative energy C field, which propels positive baryonic particles. The cosmic microwave background, according to Hoyle, an alternate explanation instead of the Big Bang, is that the CMB can be explained via carbon and iron whisker particles in interstellar space that convert starlight into photons. That is his alternative explanation for the radiation. As new data from COBE, M.I.T, and Planck demonstrated errors in the quasi-steady-state cosmology theory, various adjustments in this theory were attempted by Hoyle, Burbidge, Nalekar to match the new data. A never-ending oscillatory cyclic concept of the universe was proposed. And I do need to refer to, as recently as 2020, there was a fellow and Roger Penrose, the colleague of Stephen Hawking. Roger Penrose, colleague and collaborator of Stephen Hawking's, indicated he does not believe the Big Bang was the beginning of our universe. He holds the universe is cyclic, existed before the Big Bang, and will continue to exist after our current universe. Penrose believes evidence of a previous universe can be observed in black holes and other electromagnetic areas. Don't know, maybe the James Webb satellite may provide some more information on that. So a notable modification to the QSSC theory was the adoption of multiple mini bangs versus one initial Big Bang. So here is the situation where perhaps Hoyle borrowed from Big Bang theory and incorporated a series of mini bangs. And to the right is a graphic from a book that Hoyle wrote with Burbidge and Nalekar, A Different Approach to Cosmology, giving a sort of graphic representation of what a cyclic universe might look like. Next slide, please. Well, I just went that slide, so we can go to our next one. Okay, so I'm going to give a critique between the Big Bang and the steady state, quasi-steady state. So the Big Bang initially stated all the elements were created at singularity. And the Big Bang later seemed to adopt the concept of nucleosynthesis. A lot of work done by Fred Hoyle. And I guess here at this point, I'm also going to mention an article that appeared in the May issue of Sky and Telescope. And it was entitled The Lithium Problem. And I suppose a lot of us do get Sky and Telescope, but it makes some interesting observations that the Big Bang does not seem to adequately explain the concentration of lithium in the early universe. But let's go forward from here. There's a quote by George Gamow, who was an early, very vocal supporter of Big Bang. And he indicated all the chemical elements were created, quote, in less time than it takes to cook roast duck and potatoes, end quote. Well, I think that one was perhaps an overreach. The lighter elements certainly seem to have been created during the early moments of our current universe, but the heavier ones via nucleosynthesis in stars. So Lemaitre-Friedman models utilize Einstein's cosmological constant. And this cosmological constant, Einstein considered his biggest mistake. So actually, I'm going to skip down to the steady state below. Hoyle offered an alternative to, without using the cosmological concept. He believed there was a negative energy C field, which would repel positive baryonic matter. But going back up to the top, we're going to just finish off. The Big Bang initially gave an age of the universe which conflicted with the older known age of the Earth. This was probably due to an error of Edwin Hubble. The Hubble constant has been variously adjusted over the years. And the error initially, I believe, was due to the type of Cepheid variable star that he used did not account for interstellar dust and led to age miscalculation. Another age discrepancy in Big Bang, existing ancient globular clusters seemingly was at odds with the creation Big Bang singularity. Does the Big Bang adequately explain dark matter and dark energy? Does the Big Bang theory explain the high energy phenomenon of quasi-stellar objects and active galactic centers? So, I believe what we have perhaps is, this is all a work in progress. The steady state, quasi-steady state, I mentioned the negative energy C field. So down here we have Martin Ryle research data. He did radio telescope studies showing a large number of distant radio sources, which was in conflict with the number predicted by steady state. And again, cosmic microwave background radiation measurements by COBE, M.I.T, and Planck seemed counter to the quasi-steady state cosmology. And so the quasi-steady state cosmology later adopted multiple mini-bangs. So here we have two theories, and they both are borrowing from one another. And perhaps at some point, there'll be a refinement and an agreement between the two. That's a speculation on my part. Next slide, please. Okay, we read George Gamow's quote. We can go to the next slide. So we're going to get into some of the more controversial topics, presentations of Fred Hoyle. Panspermia, viruses from space, which is a timely topic today, given the pandemic. Darwin and the origin of species. Organic matter present throughout the universe. Time. Hoyle makes some interesting speculations on time, past, present, and future influences. Next slide, please. So it's a graphic. And is there, in fact, viable organic matter in interstellar space? Next slide, please. Viruses from interstellar space. Hoyle maintained viruses can survive in interstellar space and can survive atmospheric entry. These viruses inject their DNA code into various hosts and can alter evolution. Hoyle maintained influenza viruses, epidemics, can be attributed to sources outside our planet. And there's a page insert showing a graphic representation of a virus attached to a cell. And next slide. Another page insert. So the one on the left is from The Intelligent Universe, a book that Fred Hoyle wrote, a very good read. And the darker images are actually slide cross sections from a meteorite. And the inset, the lighter image, displays a double cell-walled virus. And Hoyle maintained that there can be a similarity drawn between the active virus, the light image on the left, with what's inside meteors. The image on the right There was a fellow, Hans Dieter Flug, 1984, who also did research. And he did not widely publicize his findings because they were controversial, and he did not want to be outed, so to speak, from the scientific community by insisting too strongly that this picture here, also showing the dark image cross-section in a meteorite with the later image of a live virus, that viruses can actually survive entry through the Earth's atmosphere. Next slide, please. This is an article in 2018 from the New York Times. Viruses attached to a fragment of a bacterial cell wall. Viruses modulate the function and evolution of all living things, scientists wrote last year, but to what extent remains a mystery, end quote. Next slide, please. This is from the same article. An international team of researchers set out 4 buckets to gather a shower of viruses falling from the sky. Scientists have surmised there is a stream of viruses circling the planet above the planet's weather systems, but below the level of airline travel. How they got there is a speculation. Why there isn't something above the level of airline traffic, I don't know. But the scientists calculated some 800 million viruses cascade onto every square meter of the planet. Interesting study. Next slide, please. So here we have a famous fossil, and I'm going to do my best pronunciation of this reptile bird, Archaeopteryx. And Hoyle felt this is another one of his controversial statements. He felt this fossil was a fake. He felt somebody embellished the feather aspect of this fossil later. And as was proven, as technology improved, I think the early 2000s, technology did in fact prove this is a genuine fossil in all its aspects. So Hoyle, to coin a phrase, ruffled some feathers in the scientific community with his position that this was a fake fossil. But nevertheless, Hoyle persisted in saying that there really wasn't a clear record in fossil history of species evolving from one form to the other. He seemed to feel that there was a biological genetic storm that arrived from outside our planet, viruses perhaps injecting their DNA into living organisms here on Earth, which caused a very rapid development of species. Next slide, please. The likelihood of the formation of life from inanimate matter is 1 to a number with 40,000 knots after it. Hoyle makes a calculation. It is big enough to bury Darwin and the whole theory of evolution. There was no primeval soup, neither on this planet nor any other. And if the beginnings of life were not random, they must therefore have been the product of purposeful intelligence. So a couple of takeaways from this slide. He did some calculations saying if there was a perhaps primeval soup on the planet, he calculated something to the effect it would take a ridiculous number of lightning strikes into this primeval soup to create viable amino acids. The other takeaway from this slide, Hoyle was accused of being an atheist in his opposition to the Big Bang. And he throughout a lot of his books and presentations, refers to intelligent design and purposeful intelligence. So I do not believe Hoyle was an atheist. He believed that there was purposeful intelligence behind life. Next slide, please. And so here are three papers and available online. They're in the public domain, and I think this gives a good representation of Hoyle's thought. So Chris Elledge will be posting the video online after the meeting, and these are available sources for people to delve into. And I will point out at the bottom the synthesis of elements in stars, the famous B²FH paper. A lot of the formulas in math is above my pay grade to understand, but it goes into quite detail, which spells out the process of nucleosynthesis. Next slide, please. I'm just listing, if folks are interested, there's a selection of books that Hoyle has published. He also wrote many sci-fi books. Next slide, please. So these are the references that I used for the presentation, things that I've read. And I have annotated 3 red asterisks. I actually had mentioned the universe, past and present reflections, which was appeared in the annual review of astronomy and astrophysics. That's available online. Fred Hoyle, The Intelligent Universe, is a very interesting book. And Fred Hoyle, Home is Where the Wind Blows. That's his autobiography. Next slide, please. Levine, any questions that I might possibly answer?
That was awesome, Phil. Thank you. You know, my favorite part of the whole story of Fred Hoyle, we had this discussion, is the whole idea of nucleosynthesis in stars. I find that just absolutely fascinating. And I wonder nowadays, I wonder if I mean, Fred Hoyle passed away in 2001. And I wonder if he'd lived long enough to enjoy what we know today, as far as, you know, the advances in our understanding of dark matter and dark energy, and also more exotic mechanisms for synthesis of heavy elements, like the collision of 2 pulsars, for example, 2 neutron stars, to produce a lot of the heavy duty stuff in the cosmos. That paper in 1957 was landmark, and it really went a long way to show the mechanisms by which most of the elements could be formed in stars. And I am particularly fascinated by the idea of quantum mechanical tunneling. It goes back to for those who studied that sort of thing in college, they always bring up the classic particle in a box. Imagine a particle, think of a marble in a box with infinitely high walls. And in the common everyday world, that particle has no way to escape the box because the walls are infinitely high. And in the course of stars, it was mentioned in the video, that infinitely high wall is the barrier of electron repulsion. You have 2 positive protons, hydrogen nuclei, that are coming close enough to each other that before they can fuse into the next element up or enter into any kind of fusion process, are repelled away from each other by electrostatic repulsions. And if it weren't for quantum mechanical tunneling, where they talked about the wave nature of those particles that are moving at high speeds have a dual nature. They have particle properties and they have wave properties. And that wave is the part that's smeared out that allows some overlap, regardless of the Coulombic repulsion, so that the atoms, the nuclei, can get close enough together to actually undergo fusion. If it weren't for quantum mechanical tunneling, we wouldn't be here.
Yep.
And and that's I think just amazing when you think that it's only been like a little over a century since the physicists Thomson discovered the electron in 1897. Rutherford knew about protons around 1913, 1915. And the neutron wasn't even discovered or at least announced until I think 1932. So look at how far we've come in the grand scheme of things. Where 100 years ago, we didn't even know what matter was made up of. And now, when I think about the paper that the B2FH paper, that was phenomenal. And you're right, it's a heavy read. I have a copy of it down the hall, and it's above my pay grade as well. It's a fascinating read. It's a giant article. I think it's over 100 pages long, and it's deep. It's pretty heavy duty. Those guys knew what they were doing, and as did others in the era. Fascinating stuff.
That's Rich.
Sure.
So, Carl Sagan did say, we are all stardust. And so it's been shown nucleosynthesis in stars producing the elements. And here we are. And I don't know if Mark Olson is still online, but he sent me a book written by Paul Dirac, Quantum Mechanics. And I'm wading my way through it because he was a fascinating fellow early in the development of quantum mechanics. Mark, you still there? Perhaps not. But
remember going through that book, Phil. It's almost people that say they understand quantum mechanics are probably they're not being truthful with themselves. It doesn't happen at this level. You don't see it happening on the kitchen table. And yet there it is buried in the kitchen table itself. I used to tell the kids in chemistry class that if you look around the room, these invisible particles that I'm asking you to believe in, these so-called atoms, they were all made in stars and other exotic mechanisms. It's almost requires a leap of faith. It requires a leap of faith to even believe that this kitchen table is made of atoms, because you can't see them. I used to tell the kids, take a gulp of your water. You just swallowed on the order of 10 to the 25th molecules of water. That's crazy. But that's what we're dealing with when we talk about, the nature of matter and in the cores of stars, where you've got very high temperatures and particles moving at very high speeds. That's where the nuclear fusion happens. And again, it's not because the particles are smashing together as particles. Don't think of them as marbles. Think of them as this fuzzball of energy that can actually get close enough together for fusion reactions to take place. Pretty cool stuff. Thanks. That was a great presentation. I appreciate that.
Thanks for giving me the opportunity.
I'll leave it open to others if any
questions I can answer, but thanks again for the opportunity, Rich.
I'm glad the technology worked out for us. It was good that we practiced it.
Yeah.
It was good that we went through it. Fantastic. Others have questions? Maybe not. This is pretty deep stuff. I wonder what Hoyle would have said. I wonder what he would have thought of the idea that the expansion of the universe is now known to be expanding instead of slowing down towards some point where his oscillatory universe might be possible. The expansion is actually accelerating due to the influence of the so-called dark energy. I wonder what he would have thought with that. I wonder if what he would have thought about pulsar collisions. Pretty cool stuff. All right, listen, I'm going to stop sharing this screen and I'm going to go back and put on my presentation again, because what I want to do is just put on the last slide if I can and officially end the meeting. Our next gathering is the June board meeting, and we're going to hold that on on June 23rd at 8 o'clock via Zoom. I'll send out the invitations to the board members. I'll send out the invitations to the membership. Members have a non-participatory role. They just get to sit and listen and watch. The next monthly meeting will be our July meeting. There's no sense in voting on it. We've had them as long as I can remember. So let's have a July meeting. Either Corey or myself will send out the meeting invitations Sunday before. And again, in closing, I would just like to really, again, thank everybody for all the help I've received over the last couple of years. I hope I've done a good job for you. I hope I leave you with good feelings and good feelings about what I did, but also good feelings about the upcoming board. I think Corey will do a great job as president with Christine Zacher as vice president. And I hope you'll give them the same support you gave me. And I look forward to serving this club as long as I can. I think it's a great organization. I love being part of it. It's been an honor to be president of the club. And again, thank you so much. And with that, I'll officially close the meeting